hopefully the kind of variety of topics that we've had in the summer school have covered sort of, a good cross section of some of the different things we hope to do with quantum computers, as well as the things that we want to compete against. Yeah, so today what we're going to do is we're going to talk about, algorithms for simulating quantum mechanics with digital quantum computers. One of the main modes that we have in mind for simulating, quantum physics using quantum mechanical systems. As you surely know, the sort of idea of using quantum mechanical systems to simulate other quantum mechanical systems, has been around for quite a long time now. People like Richard Feynman in the early 1980s, had this observation that, while quantum mechanics seems to be difficult to simulate with classical computers, if we would build a device that was quantum mechanical and use it to do simulation, that would have exactly the right kinds of features to be able to do simulation efficiently. There are different ways that you can imagine realizing this idea. One is by building sort of a mock-up of your quantum system with another quantum system and just running it. So there's this notion of analog quantum simulation that we can imagine doing with different degrees of programmability, or different degrees of control, or levels of sort of confidence in the correctness of our simulation. That's a really interesting subject that we hope to study a lot in RQS. But these lectures are going to focus on another kind of aspect of quantum simulation, which is the idea of doing simulation with a digital device. And I'm really going to imagine that we have, for the purposes of these lectures, a fault-tolerant quantum computer. So this is, perhaps kind of a tall order to actually build one. We're going to try, we're all going to try really hard to do it. But for these lectures, we're going to think about, what we could do with such a device if we had it. What are the kinds of simulation algorithms that we could run? What can we say about their performance? Asymptotically, but also, we would like to understand in more concrete terms, really what are the resources that it takes to run interesting quantum simulations, and what are the kinds of simulations that we could do with such a device. So those are kind of the topics that we would like to cover. I think Feynman, it's not maybe clear from this quote whether he was thinking about analog simulation or digital simulation, maybe both. He actually, definitely appreciated the importance of digital computation, and actually, had some results about implementing digital computations through Hamiltonian dynamics that actually we'll talk about in just a bit. Okay, so here's an outline of the kind of topics that I would like to cover in these two lectures. I'll start with some background about sort of possible applications, why we might want to care about Hamiltonian simulation, kind of a more precise statement of the problem, including how we would specify the kinds of Hamiltonians that we would like to simulate. Then I'll talk about some kind of basic complexity results related to Hamiltonian simulation. And then I'll talk about two main classes of methods for Hamiltonian simulation, one based on product formulas, sometimes called Lie-Trotter product formulas. And I'll also talk about this, and then I'll talk about a variety of, what we sometimes call post-Trotter methods, which are like things that have come after these product formula-based quantum simulations. These methods can sometimes achieve significantly better performance, at least asymptotically, than product formulas. We'll talk a little bit about the kind of relationship between the efficiency of these two methods and what we can say about them, in these two sections. And then, time permitting, at the end, I would like to talk a little bit about some kind of special topics related to quantum simulation, having to do with simulating systems with spatial locality, this idea of a simulation based on the interaction picture, and some simulation algorithms that make use of randomness. So those are kind of the things that I would like to cover. That being said, we had some great, questions and interaction during the other lectures, and I hope that we can have that here as well. So please, if you have questions at any time, don't hesitate to ask, and it's totally fine if we have to skip some of these topics near the end. Okay, great. So let's get started with some background. Okay, so what are the reasons that we might want to do quantum simulation? What are the things that we might want to use digital quantum simulators for? Well, the most obvious one is just to simulate physics, right? To do computational quantum physics. And you can imagine that any kind of system where quantum mechanics plays a significant role, where you have lots of, superposition and interference and entanglement, the kinds of features that make quantum mechanical systems hard for classical computers, any kind of system where that's the case, might be a good target for using a quantum simulator. So there are probably lots of systems where somehow quantum mechanics plays some role, but nevertheless, you can give a good classical model. And classical methods are really, can be really outstanding and do some pretty amazing things, as we heard in Thomas's talk yesterday. So, we do need to be a little bit careful about what are the targets that we choose for our quantum simulation algorithms. But definitely there have been proposals for various kinds of quantum simulation applications in areas including chemistry, condensed matter physics, and sort of materials science, and high energy physics, nuclear and particle physics. And so I think those are all interesting applications, all things that hopefully we're going to explore as part of RQS. I do think that there's a lot of work to be done to understand in really concrete terms how we would apply quantum algorithms to simulations of these problems. And I'll come back to this in the outlook at the end, but that's not going to be the focus of these lectures. In these lectures, I'm really going to focus on just the kind of algorithmic primitives for doing quantum simulation. Okay, so this is kind of the obvious application of quantum simulators, but there are some other applications of quantum simulation algorithms that I want to mention just so we can have it in mind. One is that you can use Hamiltonian simulation as a method of implementing quantum algorithms, not for simulating quantum physics, but just for other computational problems. So you're maybe familiar with algorithms for things like optimization through adiabatic evolution, or various kinds of quantum walk algorithms using continuous time quantum walks you can think of as being framed in terms of Hamiltonian dynamics. There are algorithms for evaluating Boolean formulas that were discovered through thinking about scattering processes defined by Hamiltonian dynamics. And there's a big class of algorithms now for sort of getting information about high dimensional linear algebra or systems of differential equations, these kinds of things. Also some problems related to convex optimization, that rely on quantum simulation as like the main subroutine inside the algorithm. So these are all things that, maybe don't have some obvious connection to quantum mechanics. The underlying problem doesn't have an obvious connection to quantum mechanics, but they're algorithms that have been discovered by thinking about Hamiltonian dynamics. And then, you can realize those Hamiltonian dynamics with a quantum simulator in order to implement the algorithm. So, these are some of the algorithms along those lines that have been discovered already. And, maybe there are more out there still to be discovered. And I think that's also an interesting thing to potentially do with, with quantum simulation. And, the sort of like Hamiltonians of the systems that you have to simulate to implement these quantum algorithms maybe don't look anything like some system that would occur in nature, but you can cook up lots of interesting things and try to use them for algorithmic purposes. And then the last kind of motivation for quantum simulation that I want to mention is this idea of sort of using quantum simulation algorithms as a theoretical tool just to reason about physics, right? So at some level, like a quantum simulation algorithm gives you some kind of, convenient description of the time evolution operator, right? It sort of tells you there's some way of decomposing, e to the minus IHT as, a nice product of operators, as a nice quantum circuit with not too many gates, and maybe it has some nice properties. And so maybe you could use these quantum circuits as sort of like, theoretical tools to say something about physics. And this is not completely a pipe dream. So I want to just mention one example, which is this paper that we wrote about simulating quantum systems with long-range interactions. You can ask about the complexity of simulating systems that have these power law interactions, and you can give more efficient simulations by sort of taking advantage of the locality in these systems. So there are these things called Lieb-Robinson bounds that sort of characterize how information can propagate in various kinds of systems, including these systems with power law interactions. And to show that, to give efficient simulations of these systems, you can take advantage of that information. You can use these Lieb-Robinson bounds as part of the analysis of a quantum algorithm to get an algorithm that has better performance. And so we did that in this paper, but we actually realized in the course of writing this paper that you could sort of use the structure of the algorithm that we were developing to actually prove better Lieb-Robinson bounds. So somehow turn the flow around and make it go in the other direction. And somehow use the algorithmic ideas to understand something about basically the physics of the system. So, now I think in this particular case, maybe subsequently better Lieb-Robinson bounds have been proven than the ones that we showed in this paper. But I think the point still stands that, maybe we can think about, taking ideas from quantum simulation algorithms and using them to say something about other aspects of physics, maybe area laws or, maybe other things. So I think this is an interesting direction. It's actually something that we specifically proposed as something that we could do as part of RQS. And I think it's something that would be really interesting to think about. Okay, so let's move on and sort of, formulate the problem that we want to solve. So we're interested in simulating the dynamics of quantum mechanical systems. And so, as you're probably aware, the dynamics of a quantum system are governed by its Hamiltonian, which is a Hermitian operator that tells you something about the energy levels of the system. And we have the Schrodinger equation that tells us how the system evolves. So if we have a time-independent Hamiltonian, then the Schrodinger equation, which says that, the I times the time derivative of the quantum state is the Hamiltonian acting on the state, we can solve that differential equation, and it just says that the state at time t is, the exponential of h acting on the initial state. So it's e to the minus iht times the initial state psi of 0. So that allows you to determine the state, at all times. And we can, of course, give a similar kind of, we can have a similar kind of understanding of what happens if the Hamiltonian actually explicitly depends on time. So if the Hamiltonian is time dependent, then we have sort of the same Schrodinger equation. Now just the Hamiltonian is varying in time. And there's not quite as convenient a way to write down the solution of the equation. You have to write it as sort of a time-ordered exponential of the integral of the Hamiltonian. Anyway, the evolution is nevertheless, determined by this equation. And you can ask about the problem of, understanding what is the state psi of t that you get by evolving according to a particular time-dependent Hamiltonian, with some given initial state. So that's kind of the problem that we would like to solve. So for most of these, lectures, I'm going to talk about the case. I'm going to focus on the case where the Hamiltonian is time independent, although there will be maybe some examples where, it's helpful to think about, the case of a time dependent Hamiltonian. Most of the methods that we're going to talk about, with some exceptions, but most of them, can be sort of adapted and used in the case where the Hamiltonian has some time dependence. And there's a lot that's been studied about sort of the algorithmic aspects of simulating time dependent Hamiltonians. Okay, so what is the problem that we're trying to solve? So by the Hamiltonian simulation problem, what I mean is the following. So we're given some kind of description of the Hamiltonian. We'll say more in a little bit about exactly how that's described. But we're given some kind of description of the Hamiltonian. We're given a time that we would like to evolve for, and then we have some state which is given to us in the memory of our quantum computer. So we have a representation of psi of 0 as a quantum state. Maybe because we were given some succinct description of it and then we figured out how to prepare that state. But just for the basic problem, let's imagine you're actually given a copy of the state in the memory of your quantum computer. So it's an inherently quantum mechanical problem. Then our goal is to produce the final state. Again, the output representation is really a quantum mechanical thing, right? So we're really trying to produce a copy of psi of t. And not necessarily exactly, so it'll be enough to produce the state up to within some prescribed error tolerance. Right? There's some epsilon. We would like the state to be right to, a part in 1,000 or something like that. Okay, so that's the problem. To make this problem, totally precise, we have to come up with some measure of the distance that describes this error tolerance, this error in the final state. And we're going to use, for the most part, what's I think a pretty standard sort of notion, which is like the worst case L2 distance. So we would like to do a simulation so that the output state of the simulation is within epsilon of the actual time evolved state, no matter what the initial state would be. So that's the worst case. It's worst case over all possible initial states of the system. And the distance measure is, the distance sort of induced by the L2 norm, right? So we look at the difference between the actual state that we get when we evolve the system and the state that was produced by the simulator on that given output, on that given input psi of 0. We demand that the distance between those states is at most epsilon, no matter what the initial state might have been for the computation. Okay. All right, so that's the sort of notion of error that we're going to use. Another way of thinking about that is that we're asking that the spectral norm, the spectral norm of the difference between the actual evolution operator, which is, either the minus IHT in this time independent case, and whatever is the simulated, the operator that describes the unitary operation applied when we do the simulation, the difference between those things should be at most epsilon, in terms of the spectral norm. So like the largest eigenvalue of that operator should be at most epsilon. Okay, great. So there are certainly alternatives that you could come up with to this measure of distance. We could talk about notions of simulation that actually depend on what the initial state is, and maybe you could perform better if you take information about the initial state into account, or maybe information about a subspace that it lives in, or maybe we assume that it's drawn from some distribution, and we only want some kind of average case notion of success. So all those kinds of things have been studied, and probably other things also could be studied. You could also change the norm. So and actually maybe later we'll mention cases where the simulation is itself not necessarily a unitary operation, but it's a quantum operation where some different operations are applied with different probabilities. And then maybe you want to use something like the diamond norm to measure the quality of the simulation. And you could imagine doing, using other distance measures to quantify the sort of quality of your simulation. But for the most part, we're going to stick with this kind of simple notion, which kind of covers the worst case, and I think is pretty natural. And now our goal, once we've said that this is the kind of the task we would like to achieve, now our goal is to understand the cost of doing this as a function of various parameters. So as a function of the amount of time we want to evolve for, as a function of the error that we allow, and as a function of various parameters of the Hamiltonian. So like maybe the number of spins that it acts on, or things characterizing how local it is, or we'll talk about sparse matrices and we can ask about how sparse it is. So various parameters of the Hamiltonian, could go into our, characterization of the cost of the algorithm. And when we say cost, there are different things we could think about. For the most part, we're going to think about circuit size. So how many gates are there in the circuit? But we can also think about, circuit depth. So how much time does it take to implement the circuit if we allow doing gates in parallel when they act on different parts of the computer. We can talk about query complexity, and actually we will talk about that when we talk about sort of query models for Hamiltonian simulation. So again, there's kind of various measures you can use of the cost of your simulation. Okay, so and I should say, like, if you actually want to do a simulation, in practice of some real system, you probably want to take into account also the cost of preparing whatever that initial state was. And also, making some measurement at the end that gives you some useful information about the system. So those are definitely important aspects of the simulation problem, but we're not going to talk about them so much here. Although I will just say that understanding how to simulate dynamics is also relevant to these things. So if you want to prepare quantum states, sometimes it's useful to do that by some adiabatic evolution, according to some Hamiltonian dynamics. If you want to make a measurement at the end, well, maybe it's a measurement of the energy of your quantum system, and that's closely related to simulating dynamics. So you can do that, for example, by applying phase estimation to a simulation of the evolution operator. So it's, having a good simulation of Hamiltonian dynamics is also useful to these preparation and measurement tasks as well. Did you have a question?
Yes, sir. Do you foresee quantum machine learning helping with either the computation simulation state or helping determine the soft simulation?
Yeah, that's an interesting question. So there have been some studies of trying to apply machine learning to come up with better algorithms for Hamiltonian simulation, like to learn circuits for Hamiltonian simulation. There's some evidence that maybe that would be a fruitful thing. I think it's not well explored, so I think it's not clear the extent to which that'll be useful. I could say also that, I mentioned, this idea of using simulation algorithms for other tasks. I mean, there are proposals for quantum machine learning algorithms that use Hamiltonian simulation sort of as a subroutine. So, also going the other direction. Yeah. Okay, great. Any other questions? Okay. All right. So now let me say a bit about how we, how we specify Hamiltonians in Hamiltonian simulation problems. So we have to describe how the Hamiltonian is specified to make this problem completely well defined. And one very natural model that we're going to use a lot is the model of what we call k-local Hamiltonians. So we say that a Hamiltonian is k-local if you can write it as a sum of terms where the terms act non-trivially on at most k qubits. And so that means that somehow the Hamiltonian somehow acts locally, although not necessarily in a spatially local way, just in the sense that the individual terms of the Hamiltonian act on not too large a piece of the system. So there are many advantages to considering such Hamiltonians. Maybe first and foremost, because physics is local, most of the kind of natural Hamiltonians that we'll think about simulating have this kind of k-locality property. Also, these are Hamiltonians that we can specify succinctly, right? So whereas a completely general, Hermitian operator on the 2 to the n dimensional space of n qubits definitely cannot be written down, efficiently. There is always an efficient explicit description for a k-local Hamiltonian because there are at most n choose k, possible terms that you can have that are k-local. So, and they act on spaces of, if k is small, they act on spaces of small dimension. So you can actually just like explicitly write down a k-local Hamiltonian as long as k is not too big. And this decomposition of the Hamiltonian into a sum of terms is a nice thing to have if you want to come up with a simulation algorithm. So we'll definitely make use of that kind of decomposition, in our simulation algorithms. Okay. There is, however, a more general class of Hamiltonians that's useful to think about when coming up with Hamiltonian simulation algorithms, and this is the notion of sparse Hamiltonians. So we'll say that a matrix is D sparse if it has at most D non-zero entries per row. H is a Hermitian matrix, so row sparsity kind of also implies column sparsity. So I'll just say rows to be just sort of arbitrarily, but of course this also means that it's sparse in the column sense. And so, this is kind of a picture of what a sparse Hamiltonian might look like, where the white squares are 0, represent matrix elements that are 0, and the colored squares represent, non-zero values with different colors representing, different values. And then what we would like to have to be able to have a good handle on such a sparse Hamiltonian, to be able to simulate it efficiently, is an additional property, which is that it's what's sometimes called row computable, which means that in any given row, we can find where the non-zero entries are. So let's say we can ask, where is the jth non-zero entry for some j that we specify? So where is the first non-zero entry? Where is the fifth non-zero entry, et cetera? And we have some black box, some function that we can efficiently execute that will tell us what is the location of that non-zero entry, and also what is its position. So for example, we could say, for that row, which is maybe the fourth row of the matrix, we can ask where is the first non-zero entry, and it will tell us what's the index of that location. And we also have the ability to find out what is the value of that matrix element. Okay, so that's a maybe somewhat more abstract kind of description of a class of Hamiltonians, but it has the advantage that it's more general. So this generalizes local Hamiltonians. A k-local Hamiltonian, if it has L terms, you can show as D sparse, where D is like 2 to the k times L. And this is also a class of Hamiltonians that, although it's broader, can still be efficiently simulated. And it also, although it includes local Hamiltonians, it includes many more kinds of Hamiltonians. Lots of Hamiltonians that have, sparse connectivity graphs, like ones that you might consider in quantum walk algorithms, in some kinds of simulations of quantum chemistry. So it actually does describe Hamiltonians we might like to simulate that go beyond the local ones. And another thing that's nice about this model is that because we have this black box description of the Hamiltonian, it's useful for proving lower bounds on the cost of Hamiltonian simulation algorithms. It allows us to, prove some query lower bounds, including ones that we're going to talk about in just a moment, that let us establish limitations on our ability to simulate Hamiltonian dynamics. Yes? Yes. Right. So the existence of that oracle would have to depend on some additional structure, right? So the nice thing is that we've got this model. We can just imagine we have that box and just sort of run with it. But yeah, if you want to sort of implement that for some sparse matrix, that sparse matrix had better have some additional structure that allows you to do that actually efficiently. I'm not really answering your question. I'm just saying, yes, that's an issue. And there are some cases where you can sort of, handle it. And there's another question.
Motivate, it's a general model actually, right?
Yes.
You're going to something exponentially complex. So can you enlarge me a little bit on what sense this stuff? I guess it generalizes from different methods, but in quantum chemistry, to write on a Hamiltonian is very simple, right? So you don't need exponential information to do that.
Right.
So where do you go beyond sort of, whether it would be helpful, or is it just a concept that you use because he's just putting on the time, it doesn't help you in this case anyway, or why you go to this?
Yeah, I think because you can imagine, situations where you might have this sparsity and not locality, right? So for example, in these, some of these quantum walks on kind of, exponentially large graphs with sort of, low degree, vertices. So every vertex is connected to not too many others. If you have some description of the graph that allows you to efficiently find what the neighbors are, then this is exactly the kind of, Hamiltonian that you can implement efficiently. I think there also have been proposals in kind of a quantum, chemistry setting where you have, you have a bunch of orbitals and you have an understanding of, the sort of overlaps for the Hamiltonian between these orbitals. Those are things that you can efficiently compute. And if you actually have sort of a, sparse situation in which an orbital doesn't have significant overlap with too many other orbitals, and you can figure out which are the ones for which you have to, for which you have non-zero overlap, then you can implement these kinds of Hamiltonians. So, yeah, I mean, I would say mostly it's like a theoretical device that lets you do something more that's sort of only more general, but I think there are some cases where it's actually useful to be able to do these kinds of simulations. Thanks. All right, great. So, great. So I want to talk a little bit now, before we get into sort of the discussion of explicit simulation algorithms, I want to talk a little bit abstractly about the complexity of quantum simulation. So how hard is this quantum simulation problem? So a classical computer cannot even represent the state efficiently. So, we might say, surely simulating Hamiltonian dynamics in general is just classically hard, and I think that that's true. But to make this statement more precise, we have to be a little bit careful, because the way that I formulated the problem has a quantum input. So, we can't imagine, giving that quantum state to the classical computer. It has an exponentially large description in general. So, how can we make a fair comparison between, classical and quantum attempts to simulate quantum dynamics? Well, what I'm going to imagine is that we sort of make everything, in a form that's friendly for, for classical computers. So let's imagine that we have succinct descriptions of, the input state, the Hamiltonian, and the final measurement in terms of, things that a classical computer could get a handle on. So maybe the initial state is just the zero state, or it's some kind of, it's a product state, or some kind of state more generally that you could, maybe produce by a small depth quantum circuit acting on the zero state. We could say that the Hamiltonian is, let's say, a k-local operator, and that the final measurement is some kind of, nice measurement. Maybe it's a measurement in the computational basis, or measurement of the individual qubits in some basis. Now, if we make all of these further specifications, then definitely a quantum computer can efficiently sample from the output distribution. So that's okay. But now we can ask, really, how hard is this question for a classical computer? And the answer is probably very hard. And another sort of formal way of saying this is that this problem is sort of as hard as doing anything that a quantum computer could do. So in the kind of complexity theory jargon, we say that this is a BQP hard problem. So what that means is that, any quantum circuit can be efficiently simulated by these kind of local Hamiltonian dynamics with these additional, restrictions about sort of the description of the Hamiltonian, the input state, and the final measurement. And this actually follows, he didn't describe it in exactly these terms, but this follows quite straightforwardly from some ideas in one of the two papers that Feynman wrote about quantum computing. So not the one that he wrote about quantum simulation, the other one gives a construction that kind of describes how to do exactly this. So I'm going to describe basically that construction now. So imagine we have some circuit, some quantum circuit consisting of a product of 2 qubit unitary gates. Now what we're going to do is we're going to add what we call a clock register. This is like an Ancilla register that records the progress of the computation. And we're going to write down a Hamiltonian, which is a sum of terms, one for every gate in the circuit, where what those terms in the Hamiltonian do is they advance the clock from one step to the next and apply the corresponding gate in the circuit. Now that is not a Hermitian operator, right? So to do that, we have to add the Hermitian conjugate, right? We're going to add also the operator that kind of undoes the computation. We're going to add the thing that makes the state go back from j to j minus 1, and then applies U dagger to the register that stores the kind of the state of the computation. So that's now a Hermitian operator. Also, by the way, we're going to add up these terms with some coefficients that we're going to choose carefully that I'll describe in a moment. And now, we have this Hamiltonian in which advancing the clock from one state to the next corresponds to applying, a gate of the circuit. And now you can show that with an appropriate choice of these coefficients, you can make the time evolution of the state implement the computation. And so now if we are able to give some representation of these clock register states that are sort of nice with respect to locality, then we can make the overall Hamiltonian local. So in particular, if we choose a unary representation of these clock states, J, then we can implement the transition from one clock state to the next with a 2 qubit operation. And then this overall construction if the gates are also, two qubit gates, the overall construction specifies a 4-local Hamiltonian. Okay, so this is a kind of a description of a Hamiltonian that, by running the dynamics of that Hamiltonian, you can implement any quantum computation, right? So you could take a gate decomposition of Shor's algorithm, you could, turn it into a Hamiltonian for which simulating the dynamics of that Hamiltonian, starting on some simple initial state and then making some simple final measurement would allow you to factor, right? So that kind of shows you that this problem of simulating Hamiltonian dynamics is, probably hard for classical computers. It's hard as long as there's anything a quantum computer can do, that a classical computer cannot. Yes?
I'm not too sure how to think about what the state J is. Is it like, for example, simple product state spins?
Right. So here, J, at the beginning of the slide, J is just an abstract index. But then when I say we want to represent it in unary, what I mean is we want to give a representation that lets us somehow implement these transitions efficiently. So what you can do is you can have J be basically like J1s followed by, if there are so I guess there's K states. So we're going to need maybe strings of length K. So maybe there's, J1s followed by K minus J0s. Right? It's just that bit string. And then, basically what you have to do to flip J to J minus 1 is you have to, in a place where you have a 1, 0, you have to turn that into a 1, 1, right? So that's like a 2-qubit operation. Other questions? Right, so the only thing that's not really spelled out here still is this choice of the alpha J's. So I want to mention how you would choose these alpha J's, because it's kind of a nice trick. It's like a little bit of a kind of technical detour, but there's a nice trick there. I'm going to explain that trick, and we're also going to use that trick in the next complexity result. Okay, so let's think about a kind of a quantum walk on a weighted path. So, basically what's going to happen in this, BQP completeness construction is the Hamiltonian is one that kind of propagates you from one state to the next. And if you sort of write it in a basis where you kind of rotate away these UJs, it's really just a quantum walk on a path, right? It's a sort of particle hopping on a line. And what you would like to do to sort of move from the initial state of the computation to the final state of the computation is have that particle propagate from one end of the line to the other, right? So that's kind of what we would like to happen. Yeah.
So when we use the unary representation, doesn't that put us into P space?
Oh no, because it's a unary representation of values that are only as big as the number of gates in the circuit, right? So like you need if you've got a polynomially large circuit, right, then you need polynomially many qubits to represent that. That's why a unary representation is okay, right? It's a unary representation of an index of a gate in the circuit, right? So it only gets as large as this value K, which is the number of gates in the circuit, and that's something polynomially big.
It's polynomial space.
I mean, yes, you're using only polynomial space, but I mean
that's usually tough, right? Polynomial space is usually much bigger than.
No, but you have to have a polynomial size circuit to start with in this construction, right? You need to have. I'm not sure they understand. Like, I'm definitely not claiming that a quantum computer can do anything in P space, because for this, with a quantum simulation, because for this construction, you have to start from an efficient quantum circuit.
Right.
Okay, good. Yeah, please. Oh, yeah, sorry.
Hamiltonian is like nothing term in days.
Uh-huh.
Is there a way to, if it hops, it doesn't always goes to the left side, but sometimes it can go like a confusion.
Yes.
Or choose the alphas to propagate into the direction.
Yeah, exactly. And that's exactly what we're going to do on the next slide, right? That's exactly what we're going to talk about there. Yeah, I mean, so the particle is moving on a line. Maybe it's not exactly diffusing because it's quantum dynamics of a particle on a line. And well, this is exactly what we're going to talk about on the next slide. So maybe let's go there and we'll talk about this. Yeah. Okay, so yeah, this is the Hamiltonian that we have here involves these nearest neighbor transitions on a path. And what we'd like to do is move from one end to the other. And so, yeah, if we would go diffusively, well, that wouldn't be too bad because it would still take, sort of time only quadratic in the length of the path, maybe. But actually, that's not how things move kind of quantum mechanically. we have waves that kind of propagate ballistically. And so we would expect to sort of get to the other end of the path in time that only goes like linearly in the length of the path. But to make things really clean, we would like to just go exactly to the other end of the path. And if we have a wave, I must have pressed it. I think the battery must be dead because the light blinks.
Get you a battery.
Thanks.
Okay.
Okay, thanks. Okay, so great. So yeah, this quantum wave will move ballistically, but over time, yeah, I think the battery really is dead.
Yeah, I'll do it.
So I'll try to just speak up while we get a battery. So this wave will propagate ballistically in the sense that the amount of time that it takes to move a distance, d is like linear in d. But we have a bunch of sort of interference that's happening. The wave is, there's some diffusion that's taking place, and this will reduce the amplitude over time. So, we definitely will not arrive exactly at the other end of the path unless we do something careful. So let's do something careful. So here's what we can do. So let's think about how things would evolve if instead of this particle evolving on a path, it was evolving on a hypercube, right? So there's a little picture of a three-dimensional hypercube shown here. In general, the Hamiltonian is like the sum of, sigma x operators, ones that flip the individual bits. And because this Hamiltonian is a sum of commuting terms, it's really easy to understand what the dynamics do, right? Sigma x will just rotate the 0 state to the 1 state in time like pi over 2. That's an easy calculation. And so if I do this on, the n-dimensional hypercube, my n zeros will all rotate, each of them to a 1 state in time pi over 2. And so if you think about this in terms of what's going on in the hypercube, you just kind of propagate from one corner of the hypercube to the other corner of the hypercube in time pi over 2. So you're kind of going exactly from one corner to the other. Okay, what does this have to do with propagation on a path? Well, what we can do is we can think about sort of projecting down to a weighted path, where we have sort of a vertex for every state of a given Hamming weight in the hypercube. So that's what's drawn here for this three-dimensional cube. We have sort of a vertex corresponding to the states of given Hamming weight 0, weight 1, weight 2, weight 3 in this example. And we're going to make a state that's like the uniform superposition of the, all of the states of that Hamming weight and then we're going to think about the connections between those states, right? So if we start at the L0 state, we're going to stay within that subspace of superpositions over, strings of a given Hamming weight. And we can ask how the Hamiltonian evolves in that when we project down, there are basically some coefficients that describe what are the amplitudes for transitions between states of a given Hamming weight. And we can easily compute what those are. So let's do that now. So let's let, weight sub k represent the state of Hamming weight k. So it's just the uniform superposition over strings of Hamming weight k. And then we can just look at what happens when we apply the Hamiltonian on the Hamming weight k state. And what's going to happen is we're going to get some number of, we're going to get some amplitude of the state of Hamming weight k minus 1, some amplitude of the state of Hamming weight k plus 1. You can compute what those coefficients are. They basically just have to do with the number of connections you have going to the left, the number of connections that you have going to the right. And if you do the calculation, this is what you get. And so what this shows is that if we take amplitudes that kind of respect the transition amplitudes that we get on this hypercube, from this hypercube, then on this weighted path, we can make it so that there's exact propagation from one end to the other. Is there a question? Yeah.
Can I have a quick question? So is the definition of the weight unique? Like, are there any other ways of defining the weights, like based on, for example, other measures?
Oh, you mean, do you mean to achieve perfect transfer from one end to the other, or do you mean to achieve other goals?
Projection to the weighted path, like the diagram on the right. When you translate, like a set of connection.
I think in the thing that I'm describing here, the weights are completely specified. So somehow the if what we mean by this picture is that the vertices on the projection on the path down below are the uniform superpositions of the states of a given weight, then there's just a calculation you can do that tells you what those weights are.
Okay, so it's unique.
Yeah, I think they're completely specified.
Okay, thanks.
Yeah, sure.
So in this new projection, the Hamiltonian is just the transition from like between different.
Exactly, right, exactly. So.
Back from the previous construction, I construct a hypercube and then I.
Exactly, right. So I mean, I could think, if I think about sort of multiplying the bra vector, you know, weight k minus 1 from the left, basically this thing is telling me what is the matrix element to have a transition from the weight k state to the weight k minus 1 state, and also to the weight k plus 1 state. Yeah, exactly. Right, so this is basically telling me what I can take these weights to be so that I have this perfect transmission from one end to the other. So yeah, I mean, this is basically just a trick. There actually are other tricks you could use to do kind of similar kinds of things, but anyway, it's useful. And we're going to use it also in the next example that I'm going to do. So that's why I thought it was maybe worth taking the time to go through this. Okay, the other kind of complexity result I want to talk about related to Hamiltonian simulation is this thing called the no fast forwarding theorem. Right, and what this theorem says is that if you want to simulate Hamiltonian dynamics acting for time t, then you need a number of gates that grows at least linearly in t. And this is, I think, kind of intuitive. It kind of says you can't fast forward the dynamics of generic Hamiltonians. So a way of proving this in kind of this query model for black box, this query model for sparse Hamiltonians is to think about the problem of computing parity. Right, so if I am given a black box for the bits of a string of n bit, for an n bit string, and then I want to compute whether the number of ones in that string is even or odd. So in other words, I want to compute the XOR of all of the bits. Then you need to make at least n quantum queries to do that. So this was proven in a couple of papers in 1998 that are referenced here. Yeah, there's a question?
What happens here with recurrence? Because presumably in finite time, any Hamiltonian solution will get back to where it started, and this result will be false for a short period.
Right. So first of all, I don't claim that there are no Hamiltonians you can fast forward, just that you generically can't fast forward Hamiltonians. So, whenever you have some recurrence, then, if that happens sort of early on, that's something that's going to make Hamiltonians easier to simulate. But yeah, I guess there's a question here about the, what we're so I guess if we would somehow fix the dimension of the system, then I guess what you're saying is somehow true, that somehow, if we would go for times, but they would probably have to be exponentially long times, but, generically, if we would go for some times, we could make the dynamics come back to where they were, and then we could, take the time modulo, whatever that recurrence time is, and give simulations for these, longer and longer times. So I think that that's true. What we're going to consider, here, in general, we're interested in systems of very high dimension. And so I think, what you're going to see is that in the construction, actually the dimension of the system will be growing with the evolution time, right? The evolution time that we're considering is actually going to be growing with the system size. So I think that's why the thing that you're, saying isn't an issue. But I think in practical terms, since we are interested in really high dimensional systems, and we're interested in sort of, evolution times that are sort of polynomial, in the number of qubits in the system, I think that the kind of issue that you're raising, doesn't in practice let us get around this no fast forwarding theorem, right? I think that sort of idea is that somehow, if you want to simulate dynamics for time t, for the situations you're really going to care about, you are going to have to evolve you are going to have to use a number of gates that's going to, grow at least linearly with the number of, the time you want to evolve for.
So Andrew, sorry.
Yeah.
So what's weird, so, I think about exponential, I think about modular exponentiation as a Hamiltonian.
Right.
Then I can fast forward.
Yes.
Which is part of my Shor's gradient.
Right, yes.
But then also Shor has like rationally related eigenvalues. Which is leads to kind of a common recurrence. Whereas I guess most Hamiltonians, the eigenvalues are totally irrational relative to each other.
Yes.
So there can be no recurrences in general.
Yeah, I agree with what you're saying. I think in Shor's algorithm somehow, he wants to, you can imagine that it's somehow like you're effectively evolving for actually an exponentially long time, but you're able to do that exactly because you can do this fast forwarding. There's a nice paper that Dorita Haranov wrote about sort of exactly this.
Yeah.
Or maybe you know the paper, yeah.
Yeah, well, we'll talk later.
Okay, yeah.
Yeah.
Okay, great. Oh yeah, Don.
Okay, just following up. So are there results on how generic no fast forwarding is?
Oh yeah, that's a good question.
Or instance by instance? Basically.
Yeah, sort of my feeling is that it's a pretty generic thing, but I don't know of concrete results along those lines. Yeah, it's a nice question. My feeling is that somehow you would have to have a lot of structure to be able to fast forward, but that's just a feeling, not a theorem.
I have one example,
Uh-huh.
which is any Hamiltonian that I can find the eigenvalues classically, I can fast forward on my quantum computer.
Maybe if you also have a handle on the eigenvectors, somehow, right? I mean,
Yeah, I guess so. But even that, even just that I guess maybe the eigenvectors.
you probably have to be able to get into the eigenbasis.
And then what's the algorithm?
Well, because you can then write this sparse matrix where there's just the time becomes a parameter. You just apply basically the same Hamiltonian over those indexed eigenvalues. Yeah, so because you can diagonalize it, you can basically just apply individual z gates and compute it.
Okay, so let me give you an example that sort of shows in this black box world that there are, at least that there are Hamiltonians that cannot be fast forwarded. And so what we're going to do is we're going to construct a sparse Hamiltonian that sort of encodes this parity problem. So what we can do is imagine that we have, basically two paths. But what we're going to do is we're going to put in sort of crossings wherever there's a bit that's a 1. So that's shown here in an example where you have a string of 7 bits. And the idea is that now if you want to compute the parity of this string, that's equivalent to asking, is the top left vertex in this picture, is it connected to the vertex on the top right? On the top right or on the bottom right? Right? Because every time you have a crossing, you switch whether you're sort of on the top row or you're on the bottom row. And so the parity is really just equivalent to, do you end up on the top or do you end up on the bottom when you move all the way from the top left over to the right? And so since this parity problem requires a linear number of queries, and you can use evolution on this path to move from one end to the other in a time that goes like the length of the path, right? So that's something that we can make happen exactly if we choose these coefficients that we described on the previous slide. Then it must be that somehow if you give an algorithm to simulate the dynamics of this Hamiltonian that characterizes evolution on this graph, you need to use a number of gates. If you want to evolve for time n, you're going to need to use a number of gates that grows at least like n, right? So this is sort of showing that in general the number of gates the number of queries that you need to perform the simulation, has to grow at least linearly with the amount of time that you want to evolve for. Okay, so, but this is, we're interested in giving simulation algorithms that sort of will, with polynomially many gates, allow us to evolve for polynomially long times. So this is certainly not an obstacle to that. It's just sort of a limitation on how fast we could hope to make our quantum simulation algorithms. Okay, great. So this has been, a little bit abstract. So what we're going to do is we're going to move on now, and we're going to talk about some really concrete Hamiltonian simulation algorithms. But before I do that, are there any more questions about this complexity part? Okay, great. So let's now move on, and we're going to talk about kind of the most straightforward quantum algorithms for Hamiltonian simulation, which are these algorithms based on product formulas, or sometimes they're called, Lie-Trotter product formulas. Okay, so now the idea is, suppose we want to simulate some Hamiltonian, and we have a description of that Hamiltonian as a sum of terms. So it's a sum of, let's say, L terms, and it could be that it's a sparse Hamiltonian. It could be that it's a local Hamiltonian, and then you're given really explicitly such a decomposition. It could also be more generally that it's a sparse Hamiltonian, and I'll talk a bit later on about how you can put sparse Hamiltonians into this picture where you have a nice decomposition into a sum of terms. But for now, let's just imagine that we're given some decomposition like this, and we would like to figure out how to simulate H using the ability to simulate these individual terms, which are somehow simple, right? So we have the ability to evolve according to one of the HJs for maybe any amount of time that we like, because they're really simple terms. Now we want to turn that ability into an ability to simulate the overall Hamiltonian H. Okay, so the kind of high-level idea here is that we can sort of combine the individual simulations using this thing called the Lie product formula, right? So for the kind of the two-term case, what the Lie product formula says is that if you evolve for a little bit of time with A, and then a little bit of time, evolve for a little bit of time with B, and you go back and forth, then sort of in the limit that you're going back and forth arbitrarily fast, it's like having both of the two terms on at the same time. You know, even though these two terms do not commute in general, right? I mean, if A and B commuted, it would sort of be trivial. If they don't commute, then evolving according to A and then evolving according to B is definitely not the same as evolving with both of the terms on at the same time. But if you kind of go back and forth arbitrarily fast, then it's like having them both on at the same time, right? So I have kind of a picture of this. Suppose your Hamiltonian is the sum of these two pieces. You have the ability to have one on or the other on. If you sort of go back and forth, you know, kind of arbitrarily fast, then it's like you're having them both on at the same time. Okay, so that's kind of the high level idea, but we have to make this quantitative and understand like, what is the cost of this as a Hamiltonian simulation method? Okay, so let's sort of work out kind of the simplest case of this. Let's imagine that we take this product formula that's written here, this limit as, you know, r goes to infinity, and we think about just truncating to finite r. And then we ask, what is the error, right? Let's see what happens. And it's going to be useful to think about what happens when we Taylor expand sort of the left and the right-hand side of these two expressions that we want to show are close, right? We want to show basically that if we pick a large enough r, we remove the limit and we look at the expression on the left and we take a large enough r, then it's close to the expression on the right. Okay. All right. So first let's look at the exact evolution. That's, you know, e to the minus I times a plus bt. So I can Taylor expand that to second order and I get the expression that's written here. And I can also take, you know, what happens when on the left-hand side, if I just, you know, take like, let's say r equals 1, right? So e to the minus iat times e to the minus ibt. Okay, so what I do is I write out the Taylor series of, you know, e to the minus iat to, you know, second order, similarly for b. And then if I multiply those two things out, I get the expression that's shown here. And you see that it's not exactly the same as the exponential of the sum, right? In the exponential of the sum, I have the second order term a times b and b times a both appearing, right? But if I do a first and then b, or I do a on the left and, you know, b on the right, I guess that means doing b first and then a. But anyway, if I have a on the left and b on the right, then I only get the terms in the order a times b, right? So whereas I had a, you know, 1/2 ab plus ba in the Taylor series of the exponential of a plus b, I only have a, I think there's maybe a factor of 2 missing. Sorry about that. I only have a times b in the second order term for the evolution of, you know, with a on the left and b on the right. Right. So these two expressions don't agree exactly. And yeah, I'm sorry, there's a 2 missing. It should say a squared plus 2ab plus b squared. So I have some deviation at second order, but I'm getting the first order of the Taylor series right. Okay, so what that tells us is that, you know, the sort of e to the minus iat times e to the minus ibt, you know, is the same as e to the minus I a plus bt up to terms of order t squared. And so now what I can do if I want to get an accurate simulation is I can do like what's written on the left-hand side of this Lie product formula for some large value of r, right? So if I take e to the minus iat over r times e to the minus ibt over r all to the r, what's the error going to be? Well, I can just plug in, you know, t over r into the expression there on the left, and then I have to sort of add. So then I'm going to get error that's like t squared over r squared. Right, because I plugged in t over r for t. But now I do this r times, right? So with the triangle inequality, I'm going to get an extra factor of r in the error. So the error is going to be like t squared over r, right? And so now if I want to make that error most epsilon, how big do I have to take r to get, you know, a simulation that's accurate to within epsilon? Well, I just set t squared over r to epsilon, and I get that r should be like t squared over epsilon. Right, so what this says is that I can take a number of elementary exponentials that's quadratic in the evolution time. So that's kind of satisfying this no fast forwarding theorem. It's actually off quadratically. But it goes like t squared over epsilon. And that, you know, is going to give me a simulation that's accurate to within epsilon. So this idea was laid out in this paper by Seth Lloyd in 1996, which was like the first, you know, really concrete, you know, digital quantum simulation algorithm that was proposed. And it's great, right? So it has uses a number of gates that's polynomial in the amount of time you want to evolve for. It's polynomial in the inverse of the error, and so you can imagine using this to do Hamiltonian simulation. But you can possibly do better by designing your algorithm more carefully, and that's what a lot of the stuff that's coming up is going to be about. Okay, so the kind of first thing you can imagine doing to make this algorithm better is to use what are called higher order product formulas. Use product formulas that give you higher order approximations of the exponential of the sum. So let's see how you can do this. So the kind of simplest thing you could do is to use the second order product formula. So the second order product formula for a plus b involves according to time for time t over 2 for a, and then t for b, and then t over 2 for a. And if you do this, then you can show, I'm not going to do the calculation here, but you can sort of expand things out and see that you get now a second order approximation. In other words, the error is order t cubed when you compare evolution according to a plus b to this product formula. And so that's great. So now you're going to need fewer gates to do a simulation to some fixed allowed error if you use these second order product formulas. But you don't have to stop at second order. You can go to higher and higher order. And in fact, expansions to arbitrarily high order were constructed by Suzuki in the 90s, not thinking about in the context of quantum computation, but just thinking about sort of classical numerical methods. But you can, it turns out, apply these methods also in the context of quantum computing. And so he gave a construction that's described here. Actually, he gave other constructions too, but this is kind of the one that's most useful for quantum computing, that involves basically taking lower order formulas and using them to construct recursively higher order formulas. And his construction constructs formulas always of even order just because of the way that it works. It always increases the order by 2 when it goes from one formula to the next. And so if you want a nice exercise, you can try writing out a formula like this for some parameters pk and qk, and then try to find values of pk and qk that will make this a formula that's accurate to order 2k, assuming that s 2k minus 2 was an approximation of order 2k minus 2, right? And we know that s2 is an approximation of order 2, right? So if you can do this, then you can construct formulas of arbitrarily high order. So there's just some formulas you can work out for what pk and qk are, and maybe you can do that during the break if you're looking for something to do. Okay, so that gives you construction. That gives you a construction of formulas of arbitrarily high order, and then that's useful for Hamiltonian simulation, and you can work out bounds on how many gates you need in order to give overall error epsilon along similar lines to the calculation that we did on the previous slide. And so if you do that calculation, you can show the following. So if you want to simulate a Hamiltonian, and you can generalize this from the case with 2 terms to the case with L terms, if you want to simulate a Hamiltonian with L terms, and you use this order 2k approximation of the evolution operator, then you get a simulation that uses a number of elementary exponentials, so a number of exponentials of the elementary terms of the Hamiltonian, that scales close to linearly in t. So it scales like t to the 1 plus 1 over 2k, where 2k is the order of the approximation. I mean, I'd write 2k just because these Suzuki formulas happen to have even order. So that's getting closer and closer to linear in t as you go to larger and larger k. So you might think, okay, if I want to have a really efficient simulation, I should just go to really large k. And also, by the way, the epsilon dependence is getting better and better as k gets larger and larger. It's going like 1 over epsilon to the 1 over 2k. So the scaling with epsilon is sort of milder and milder as you take k to be bigger and bigger. So that sounds great. Let's just take a k that's really big, but then you notice that there's an exponential in k prefactor, right? So it scales like 5 to the 2k. So that's kind of a problem, right? That says you definitely can't just take k as big as you want because you're paying an exponential in k cost. So there's sort of a trade-off there. Is there some benefit to taking k to be bigger than 1? Well, probably, but it depends how big is the problem that you want to solve. And the fact that this prefactor is exponential means, you definitely won't be able to push to really large values of k. So if you have some particular simulation you want to do, you just have to work out like what's the best value of k for your application. But yeah, I mean, I would say from like examples that have been worked out, even for like fairly modest size systems, there really is some benefit to going to higher order product formulas. Like it's maybe worthwhile to go to 4th or 6th order, even for systems with like tens of qubits. So there is some benefit of using these higher order product formulas, but probably you don't want to use the 100th order product formula because you're going to be killed by this prefactor. Yeah. So anyway, this is sort of like what you can say about the cost of using these higher order product formula approximations. And this gives you some bound on the cost of using those approximations. Although, as we're going to see next, you can actually give better bounds on the quality. On the quality of the approximations that you get, and correspondingly on the number of gates that you need to use to do the simulation to up to some accuracy. Yes. So what happened to the odd order, right? So yeah, there's no reason you couldn't in principle have odd order formulas, but Suzuki didn't construct them, or at least this construction doesn't give them, just because it uses certain symmetries to sort of make formulas of higher order, and it just always increases the order by 2, just because of how it works. I don't think there's any reason in principle you couldn't construct formulas of odd order, but they just don't come out of this particular recursive construction. Yeah, and another question.
So you were saying that there's some optimal order because of the number of exponentials. So are there results known how to choose this order in the presence of noise?
Oh, yeah, that's a good question, but one I don't really have an answer to. Yeah, I mean, definitely if there's, if your system is noisy, that will be a problem. And you could imagine that somehow the effect of the noise would be more or less depending upon, so there is some work on sort of making product formula simulations better, maybe in the presence of noise, by sort of like adding symmetry to the, sort of the way that the product formula is applied. But yeah, I would say that's not something that's been well studied. My feeling is that it's probably hard to imagine applying these digital Hamiltonian simulation methods even to really simple systems, like sort of one-dimensional spin systems, or kind of systems with kind of very nice interactions. It's hard to imagine doing that in kind of a pre-fault tolerant regime. Like if you look at the numbers of gates that you need to do Hamiltonian simulation, even of like systems with kind of tens of spins, it's like beyond what you're probably going to be able to do without fault tolerance. So that's why I kind of tend to think about these algorithms kind of not in the presence of noise, but like it's a separate thing you have to do. First, build me a fault tolerant quantum computer, and then come back to me and we can run these algorithms, But I think it's a really great question. I mean, I think I actually have it in the Outlook slides, basically what you're suggesting, to sort of like think about how these kinds of algorithms behave in the presence of noise, and can we get away from that? Can we imagine actually using these digital simulation methods with noisy devices and tolerating the noise? So I think it's a really great question, but I think it hasn't been explored that much. Yeah.
Probably a related point. So in classical neural analysis, typically the idea is that if you go to very high order, then the stability of these schemes becomes a problem. So does that also come up true in the quantum case when you have noise, so that if you use these high order schemes, then maybe it's more just the stability of these schemes maybe just kill the problem.
Yeah, possibly. I mean, so there's actually, Suzuki actually gave another construction, which is sort of less numerically stable than this one, which uses, instead of 5 to the 2k exponentials to go to order 2k, uses 3 to the 2k. But it sort of is less numerically stable in the sense that these pks and qks sort of grow. Like with this construction, they remain bounded, but with the 3 to the 2k construction, they sort of get larger. And that actually translates kind of even in this setting where we imagine that there's no noise, translates into that construction behaving worse, the one with the 3 instead of the 5. But I guess you're making kind of a different point, which is about what happens in the presence of noise. Yeah, I mean, I think it's entirely possible that there could be such an effect. I think it hasn't been, as far as I know, it hasn't been sort of explored explicitly, but maybe exactly what you're describing, happens. And it would be a good thing to know if we want to think about, using these methods in this kind of pre-fault tolerant regime. Yes.
One comment. So actually, for these higher order, we talk about manipulation. The most important point about the Suzuki means that you can, so it shows you can go to arbitrary high order.
Yes.
I would kind of sort of caution people from using the higher order solutions because they're not particularly good. So you can actually optimize some higher order solutions, and for fourth or sixth order, you can get much better than the solutions just by minimizing the leading error term that you have in this condition. So it's more like a principle thing. You can show what Suzuki shows you can go down to the higher order, but in practice, so we use them also all the time in like classical simulations, and yeah, they're not the best sort of for it.
Yeah. So this is something that this is actually also something that I have mentioned later on in the Outlook slides. Yeah, I think this is something that would be great to understand better, like in the context of quantum simulation, because I think that maybe hasn't been worked out so much, and it would be great to know, like, what is the impact of the kinds of things that you're describing, which I guess it sounds like they're used all the time in classical methods, but I think it would be great to sort of explore more, like using them in quantum simulations and using that to get more efficient algorithms in practice. Yeah. Okay, cool. Oh, yes.
How quadratic formulas can be related to other formulas like the BCH formula, or how does that be used to develop algorithms?
So I'm going to say something in just a moment about sort of an approximation and sort of there's a connection to Baker-Campbell-Hausdorff. Yeah, I mean, I guess that's a formula that says something about sort of relates the error in relates evolution according to A plus B to sort of evolution according to A and evolution according to B sort of individually, where the error sort of comes in through a commutator. But then there's sort of the way it incorporates higher order terms is sort of not so useful from the perspective of having error bounds you can use for quantum simulations. And actually the next thing that I'm going to talk about is basically about how to get something like that from an analysis of these product formulas. So maybe that'll, it's related a little bit to your question. And I guess, so we should take a break in 5 minutes. So yeah, maybe what I'll do is I'll just talk briefly about this improved error analysis for product formulas, and I think that'll be a natural place to break. Okay, so so there are these bounds that I described on the error in these product formula approximations for quantum simulation that give you some understanding of what would be a sufficient number of exponentials to achieve some given allowed error, but numerical results sort of looking at how much error there actually is in the application of these formulas suggests that these error bounds can be very loose, right? So somehow just looking at the Taylor series and kind of adding up the higher order terms in the Taylor series to get some bound on the error can give you a very loose estimate of the error. And there's a nice way of sort of getting better bounds on the error using this idea of what's called local error analysis, which kind of arises from this paper of Lacombe and Thalmer. So basically what happens in this work is that you can give sort of nice kind of integral representations of the error in these product formulas. So you can write the difference between the evolution according to A plus B and the product of the evolution according to A and the evolution according to B. You can give some nice kind of integral representation of that operator, which I'm definitely not going to derive here, but if you go to this paper, you can find it's basically elementary manipulations to give some representation like this for the error. And this expression, notice that it involves a commutator between A and B, and then some evolution according to A and B, and the sum of A and B on either side. So that's it's basically the commutator of A and B times some unitary things. Those are norm one things. So just using the triangle inequality, this allows you to upper bound the error in this approximation by something that scales with the commutator. So this is kind of like what you would guess from the Baker-Campbell-Hausdorff formula, but that has sort of like higher order terms that it's sort of like not so clear how to bound. This local error analysis allows you really to just like see that the error goes like the commutator. So these kinds of expressions have the advantage that they don't require you to sort of explicitly sum up contributions from higher order terms. They show you that the error scales like the commutator, and the result is that you can get potentially much better performance. You can get, for some cases, sort of better understand that there's better asymptotic performance than what you would think from the kind of naive bounds, and you can also just get better explicit constants that show you that things really seem like they will perform better in practice.
So this doesn't give you a different algorithm.
Right, so this is just better analysis of the same algorithm, exactly. Yeah, and so there's a sort of another paper that sort of generalized this to give kind of a nice general theory of Trotter error, which basically, so it kind of constructs this quantity, it's called alpha here, which is like the sum of the norms of like all the nested commutators out to some depth. And you can use that quantity to quantify the error in a Pth order product formula approximation, which could be the Suzuki construction where P would be an even number, but it could also be other things that you construct. Basically any product formula that you might write down to approximate the evolution of the sum of terms, you could sort of estimate the error using these bounds. And so these bounds give you kind of better control on the error in these product formulas, kind of in terms of this parameter alpha, which allows you to get kind of much tighter rigorous analysis of product formula simulations. So for example, if you compare to sort of the empirical behavior of these formulas for like, spin models with like tens of spins, you can show that the error estimates you get from this that are sort of like totally analytical are really only off by a factor of a few, like 5 or so, for these systems. So they give you kind of much tighter error bounds that show you that these product formulas actually perform, quite well in practice. Okay, so I think that's a good place to stop for now. When we come back, we'll talk about these post-Trotter methods and some other things. Do we want to take any, are there any other questions before we go to the break? So maybe not. So